All right, so we were getting ready to prove this kind of annoying result, but important, extremely important result for, I think, making sure we have a good grasp on everything. So just to review a little bit, we've got the standard unary encoding of any alphabet. So that, I've just got an example here. If sigma is A, B, C, D, E, F, that's the alphabet, then the way we're going to encode this alphabet with just 0 and 1 is in this really stupid unary way, where A gets all zeros except for a 1 here, B gets all zeros except for 2. You get the idea. I'm not going to say this out loud. And we were getting ready to prove that you could simulate any machine that's working over this alphabet, say, with a machine that works over this specific alphabet, 0, 1. And we have to be careful with what we mean when we say that, because nothing, we're only talking about equivalence up to association of symbols at this point. So, when I say that the machine M does the same thing as the machine that works over this alphabet, we can only say that up to a specific encoding. And that encoding is this. And so the way we're going to do that is we have a machine that's doing, say, this. That we have a machine with a transition function delta that, it's looking at like this. We've got the standard kind of setup. And it transitions to something like this, where the cursor moves somewhere, transitions into some new state P, and puts a new symbol here, lambda. And so in this case, I've said, okay, sigma, that's going to correspond to this encoding, and lambda is going to correspond to this encoding, 3 ones, 2 ones, respectively. And so the idea, what we're going to build is we're going to build a machine that simulates this transition. But it's going to be complicated because one cell of the original machine is going to correspond to uh, S cells of the new machine, where S is the length of the arbitrary alphabet. So if sigma is the original alphabet, I'm going to say S is the number of symbols in it. So I'm going to have S cells to one cell, and that's what's going to kind of that's kind of what the game is going to be. Let me scroll down, kind of read off the theorem one more time, and then we'll get down to business. Okay, so let M be a Turing machine. Here's the transition function, or sorry, here's the transition function. Whoops. Then there's a machine M prime over the alphabet 0, 1, or if you prefer, blank and triangle, if you're going by my original rule set that you have to have these two symbols, which halts over the same inputs as M up to the encoding, and accepts and rejects all the same inputs, also up to the encoding. I should have put that here. And operating at the same time and space complexity. So that's the game. Okay, so let's start to prove this. I said I was only going to sketch a proof. I don't think that there's a way. I think I'm going to do this in all of its gritty detail. The proofs after this I'll sketch more so, but this fact, despite how boring it kind of is, and believe me, I don't want to do this, but it's extremely important that we get this straight before we move forward. So I'm going to go ahead and, like above, we're going to set some things up. So sigma, we're going to say, of the original machine is going to be labeled S. So there's S symbols there. And Q, I'm going to call Q, Q is this Q here is going to be, I'm going to label the symbols 1, 2, 3, dot, 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 up to L. Let's say that Q has, so Q is size L. So there's L states of the original machine. Okay, so again, I'm going to scroll up here a few times because really what we're trying to do is we're trying to simulate this silly little step. We're going from here to here. Now, I'm going to actually say one more thing first. Without loss of generality, when I say WLOG like this, that stands for without loss of generality. What I mean by this is we're going to assume something that we know we can assume. We're going to assume, so without loss of generality, we're going to assume that the machine M never stays, the machine M's cursor never stays still. So that's something I've already proven that we can assume, because I proved that for any machine whose cursor does not stand still, there's an equivalent machine that does the same thing whose cursor does not stay still. So We can assume this by the last proof that I gave you, and that'll help us just a tiny bit to simplify the headache that looms ahead. Um, so I can assume that the cursor here in this picture is going to either be here or here at the end. But this is the step we want to simulate. Maybe I'll just keep it for reference right here. So we're wanting, if I can describe how to simulate just one step of the machine in general, then I'm done, because then I can just do that simulation repeatedly. So all of this proof is going to boil down to just describing how to simulate this step, where you take where I cannot draw sigmas on this computer. Where we do this, we go into some new state. I'll put the cursor here, but it doesn't have to be here. And I'm in some new state P. And this illustrates, of course, sigma Q equals lambda P D, where D is either 0 or sorry, not 0, 1 or -1. Okay. And we're going to have, to illustrate our example, to illustrate what I'm going to describe, we will be kind of assuming for illustration, we will use the example where S equals just 5 and sigma has a correspondence with 0, 0, 1, 1, 1, and lambda is 0, 0, 0, 1, 1. And so I'm going to describe things in the abstract, and then repeatedly, as I describe things in the abstract, apply it to this kind of more particular case so that you can understand what it is that I'm describing. So, immediately what this means is that this guy here is going to look like this. So this is what this cell would correspond to. And we're gonna start by supposing that for every step we start with the cursor here on the leftmost cell. So it's gonna start here. And let me type out the plan. The plan, it's a 3-step approach. So step 1 will be scan right to figure out what symbol we're looking at. Step 2, so that's going to be like a read phase. And then we'll have a write phase. Move backward, writing in the symbol we need to replace it with. And then step 3 is move to the left cell. And I put cell in quotes because when I say cell, what I mean is like the next group of cells that simulate a single cell. So move to the left cell or the right cell, depending on D. So this is the plan. So we have a read phase, a write phase, and a move phase. That's kind of the idea. And to do this, we're going to add lots and lots of new states. Still a finite number, but it'll be a lot of states. So let's start with step 1. Hey guys, it's me from the future, and I just wanted to jump in. I think this is the right time to jump in and address a couple of I don't know if I would call them mistakes, but things that I needed to say that I didn't. So first of all, I mentioned in the statement that we're using this alphabet 0, 1. And I said, when I said that, I mentioned that you can kind of interpret these as a blank and a triangle if you want. And there's 2 things I want to address about this. So we haven't really talked much about this triangle, and the bottom line is that I overthought this triangle. Every time I go through these really low level kind of basic results one more time, I notice things that I didn't before. And one thing I think that I didn't understand was how unnecessary and kind of not fundamentally actually there this triangle actually is. We defined our standard to be a Turing machine that begins looking like this, right? Where you have a triangle, and then the input x, and then blanks everywhere else. And I think it's kind of obvious to say this, but this is just a standardization. It's not really necessary to start like this. Oh yeah, and the cursor begins here, and we're getting in a start state. Now, what's necessary here? Well, we do need infinitely many blanks, and by that I mean there is a single special symbol that is the only symbol that appears infinitely often on the tape. That's going to be a blank. Um, and because that symbol is always necessary, that symbol is going to be always this zero here. Um, in fact, the standard unary encoding of a machine language, if it has a blank, we're going to always encode it essentially with the nothing but zeros, or if you'd rather, nothing but blanks. In other words, in the simulation, we're going to assume that a cell of blanks is what we interpret as a single blank. So the zero needs to function as a blank. So when you see zeros in the following proof, you should think of these as blanks. You have to think of these as blanks. That's essential. And the standard unary encoding of any Turing machine alphabet, that is any alphabet that includes a blank, will always be this. That'll be our standard too. That's essential. What's not essential is this triangle. Um, this triangle, we have this standard of how we initiate a machine here. And I think it's pretty obvious that you don't really need this triangle there at all. It, for a two-sided Turing machine, it's just as valid to just put an x here and just start on the first kind of character of x in the S state. You do need a starting state. You do need a special designated starting state, but you don't need a designated starting position, which is kind of what this triangle does for us. You don't need that. You can just assume that we're always going to start on the first character of the input, and that is what we're going to assume. This starting kind of input, this kind of input configuration, is the more primitive kind of Platonic form of an initial Turing configuration. So the more fundamental form of a Turing machine model doesn't include a triangle and begins like this. Now in the next video, we will define a single-sided Turing machine, a Turing machine that only goes in one direction. And when in that case, this triangle does become necessary because you need an indicator of something that you can't go to the left of. But for a two-sided Turing machine, which is in many ways the more fundamental form of a Turing machine, just like erasing this triangle is, you don't need the triangle, and in fact, you probably shouldn't have the triangle there. That said, the triangle can be useful sometimes, and I think it's helpful for newcomers to understand what's going on. So I wouldn't change my original definition, where the standard is to have an input configuration like this. But once you've gotten used to kind of how things work, you should assume that this triangle really isn't there anymore, and that the Turing machine begins like this. So both of those things, I think, if you keep them in mind in the upcoming proof, you'll have an easier time understanding what's going on. So step one, that's the read phase. So what we're gonna do is I'm just gonna write out the states. So we're gonna have a bunch of read states. So have the a squared L. Oh wait, sorry, S squared L. S squared L many read states. So that's a lot of states. But the number of states that I'm defining here depends on the alphabet size of the original machine and the number of states of the original machine. So it's going to be like, I'm going to label them like, so we have R001, R002. I'm going to have three kind of sub-indexes for each of these states. And it's going to dot, dot, dot like that until I have L. I guess it's actually more than S squared L because I started 0 and go up to S. It's really like S plus 1 squared L. But it's a bunch, but finite and dependent on the number of stuff. So the first two indexes kind of count up to S, the number of symbols, and then the last one counts up to L. And so the idea is going to be that we at any point we're in a state L, right? But in order to actually know what to do, we also have to know what the symbol is. So I have to kind of keep track of the state that I'm in while moving right and counting the number of. I need to count two things, right? I need to count first off how far I've gone so that I know when I've reached the end of a simulated cell, and then I also need to count the number of ones so that I can figure out what symbol I'm looking at. And that's why we're going to have two different subindexes for S here. What that means is like this is going to be the one that counts. So this one keeps track of uh, uh, where I am so as to stop when I've reached the end of a cell. And then this one keeps track of uh, how many ones so as to determine the symbol that I'm looking at. And then this keeps track of the state. Keeps track of the state of these are all states, right? But this is going to be this index is just basically here to keep track of which state I'm actually simulating, of the state I'm simulating. So that's the idea behind all these states. So now let's define what's going to happen. So first of all, um, I'm just going to write it out. So suppose we're looking at a 0. So define delta prime to be m prime's transition function. M prime's possessive apostrophe. M prime's, oh my God, the simulating machine's transition function. I probably don't need to write that, but you know. So I'm going to say that delta prime of 0, let's suppose I'm looking at a 0, and I'm in the right pit, I'm in the right state I, J, Q. So I mean, I'm going to be in state Q, right? The idea is that I'm in state Q, and so I'm just going to keep the Q here. The Q is not going to change during the right phase, but I need to keep track of it. So I'm looking at a 0, I'm in state IJQ. What I'm going to do is it's the read phase, right? So I should probably leave the symbol alone. Um, and then if it's a 0, then that means that that cell in the simulation cell does not count towards the symbol that I'm looking at. So I'm just going to increment I. So the state changes. It goes from state IJQ to state I plus 1 JQ. The J is left alone, the I increments, and that's that. And then also delta prime of 1 RIJQ is going to equal, still leave it alone, but now I'm going to increment both I and J. So that's what's going to happen. So now I'm counting the ones, and I'm also counting the steps that I've taken. And that's how it's going to go up until the end. So let's draw the effect of this. So for all Q equals 1 dot 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 L, for all I, J. Okay. Um, I guess it's S minus 1 because you're going to increment up. Okay, so that's that. Um, and so what's the effect? Let's draw this effect. So in our particular case, what's it going to look like? Well, oops, it's going to be a 0, 0, 0, whoops, 1, 1, 1. And I'm going to be looking here, and I'm going to be in the read state 0, 0, Q. So let's see what the effect of these definitions of the transition function are going to accomplish. Well, if I'm looking at a 0, then I increment the first thing. So I jump to here, and now I'm looking at R1, put lines, R1, 0, Q. But I don't increment the 0, right? And then I jump here, and now I'm in R2, 0, Q. And then I jump here, now I increment both, right? So now I'm in R3, 1, Q. And then I jump here, and now I'm in R4, 2, Q. And then I jump here, actually, I jump one more. So there's going to be something in that cell, who knows what it is. And at that point, I'll be in R5. And I need to jump one more time so that I can count this 1 if it's a 1. So that's going to be 5, 3, Q. And that's when to stop. So I know when to stop now because I've hit the end. I've reached the maximum number here, 5. And at this point, I also know what symbol I have. I know that a 3 corresponds to a sigma. So now I have now I have the symbol state pair. Right here, now I have the symbol and state. So that's what that's going to accomplish. I now need to transition into a writing stage. Yeah, so the write phase is going to be more complicated, but the idea is that I need to run backwards, erasing essentially, or adding in ones to change the thing. So that completes the read phase. Now we have the write phase. So the write phase is going to be more complicated in a sense. So have states W 0, 0, 1, negative 1, W 0, 0, 1. So it's going to be kind of the same, except I'm going to have two. I'm going to have the same number of states times 2, right? I had I had S squared L states here, or something like that. I'm going to have double that here because I also want to keep track of the direction now. So it's going to be double. So this is going to be the direction. 2, negative 1, dot, 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 W, um, S, S, L, negative 1, and then it'll start over W, 0, whoops, 0, 0, 1, 1, dot, 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 W, S, S, L, 1. So overall, 2 times S squared L many-ish states. I think it's still S plus 1 here, not S. Whatever. It's a bunch of states, but it's dependent on the machine itself. It's not dependent on the input or anything. So by the time we've gotten to this, we're gonna have, like, in general, this will be some number I. So we'll have state R sub S I Q, where sigma corresponds to 0, 0, 1, 1, 1. And so if delta of sigma Q is equal to lambda P D, then I'm going to want to change this. So I needs to change to a J. So let J code the number of ones in lambda. So if I set up here that lambda, I was going to kind of, in the example, I was going to do sigma 0, 0, 1, 1, 1, lambda 0, 0, 0, 1, 1. So then J would be 2. So I would kind of want to transition from 3 to 2 based on the 3. So I would have a 3 here, and then that would tell me to transition to a 2. So uh, that's going to, so what's going to happen then is what I want to do is I want to transition to a write phase while moving left, and put a J here and a P here. So define delta prime of anything, 0 or 1, it doesn't matter what. I jam both definitions together. R S I Q to equal 0 or 1. Just leave it alone. What it leave alone. Uh, with a yeah 0 or 1 comma, and then I'm transitioning to a right phase. I'm going to leave S alone. I think. I think I want to leave it alone. Yeah. Leave S alone. Uh, I'm going to put in the second index. That's going to indicate the number that I want to write in, J. So that tells me how many ones, and that's there based on the I. Q is going to be replaced with P. This is the new state. I want to keep that information. So these two pieces of information yield kind of these two pieces of information. That'll be hard coded into the new machine, just like this is hard coded into the old machine. Um, and then D, same thing. That'll be hard coded, and that'll be a number, either 1 or -1, and also go left. So what's that going to produce? So in my example, currently I'm here. I'm in the read phase, 5, 3, Q. And what that's going to do is I'm going to transition over here. I'm going to move one to the left. Um, so I'm going to that what this command is going to do is it's going to move me over here, and it'll put me in the state W5, 3, or sorry, 2, because J is equal to 2, 2, uh, P, whatever P is, and then D, whatever D is. So that's what's going to happen. And now I need to start to move left. And what's going to happen is I'm going to decrement the top this number, just like I incremented it to keep track of where I was up there, while also writing in ones and decrementing this until it gets to 0, in which case I stop writing ones and I start writing zeros. So that's the idea, is like, so decrement these, add ones until J equals 0, then add zeros. So that'll write in the new number, and then keep these two things the same. So let's write that in. So with that, to kind of translate that into machine code, delta prime of, let's just say like anything, doesn't matter whether it's 0 or 1. We don't really care about the actual contents of this, right? We're just writing in numbers now. We know what to write in, so we don't really need to care whether this is 0 or 1. It's going to be the same. It'll be the exact same command that I'm going to write, whether it's a 0 here or a 1 here. Um, that's different than what was up here. I wanted to leave the input alone up here. Here, I'm not going to leave the input alone. I just don't care what it is. Um, so W I J P D is going to equal. Whoops, gotta close the parentheses. Is going to equal. It's going to write in a 1. So this is the case that J is greater than 0, and I is greater than 0. So it's going to be, I'm going to transition to the state W, I minus 1, J minus 1, P, D. So P and D stay the same, and I move left. For I greater than or equal to 0, or sorry, just greater than, I think, 0, J greater than 0, and that's that. And then we say delta prime of anything again, Wij. And so, if now I'm going to look at the case where I is greater than 0, but J is, sorry, I just wrote I twice there, didn't I? I is greater than 0 and J is equal to 0. J is greater than 0 too. Now J is going to be equal to 0, so I'll put a 0 in the subscript P, D. If that's the case, then I want to write in a 0, and I only want to decrement, obviously, I. So leave J alone, or at least, and by that I mean leave it at 0. Keep P and D. I just need to keep that information for later, and keep moving left. And so what that's going to do, so here's the effect of that. I guess I can draw the effect up here. So the effect is going to be, it's going to move here, and then I'm going to go into W4, 1. So I write a 1 in here because I see a 2 here. It's not 0. And then I move left, and I end up with a 4 and a 1 here, and it's still P and D are the same. And then I move here again, and now I have a 3 and a 0, and a P and a D. Now that I have a 0, I write in a 0. Um, Actually, I think I made a mistake. I mean, yeah, this should have been a 1 to begin with, right? Because I'm still in the right phase. I haven't rewritten it yet. So I write 1s technically here, but they're there already. Now I've gotten to this, and I see a 0 here. So I move left, and I replace this with a 0. And now I'm in state W2, 0, P, D. And then I move left again. And now I'm in W1, 0, P, D. And then I move left one more time, and I'm right here, and I'm in W0, 0, P, D. Okay, so I've rewritten these two commands, I mean, these are not two commands, they're a bunch of commands, but I'm writing it in a compact way, so that this is still for I greater than 0, by the way. When I is equal to 0, I'm going to need to transition into the final phase, which is the move phase. But I mean, I've gotten the right stuff. I've done that part. I've written in the correct symbol. So let me just write in. Let me draw the tape one more time so that we have the effect and know where we are. So we are now left with I'm looking at something, but I don't really know what. And over here, I have I have now the coding for the thing I wanted to replace. So I have now successfully written uh, uh, the code for lambda in the place of sigma. And I'm pointed here, and I'm in state W0, 0, P, D. And note, I still have the new state that I want to start the next step in, and I still have the direction that's going to tell me where to move. So now I need to move. Now I need to think about moving. So step 3, moving, moving the cursor. Obviously, I'm moving the cursor this whole time, but from the perspective of simulating one step, I haven't moved the cursor yet at all. So so if d equals 1, let me just so if d equals 1, what do we want to do? If that's the case, then we want to move forward. How many cells? Let's think. In the case of this guy here, I would want to move 1, 2, 3, 4, 5. So that's the number of cells equal to a cell, like a simulated cell size. But then I want to move forward one more time because that would put me in the beginning of the next cell. So I don't want to just move S cells. I actually want to move um, S plus 1 cells. Um, enter into a new reading cycle. And then okay, so that's the case d equals 1. And then if d equals 0, want to move backward. How many cells again? Now I end the right cycle. If I'm needing to move I always end in the last cell of the previous simulated cell. So I need to move backward actually less than before. So how many is that? Well, I think it's S minus 1 cells. Yeah, need to move backward S minus 1 cells, then enter into a new read cycle. If I move S minus 1 cells, then that'll put me in the place that I want to be. So different distances that I need to move depending on whether I'm moving left or right or simulating a move left or right. And so we do need to kind of address this in two different cases. So case d equals 1. And this video is going kind of long, so maybe I'll only do this direction, and then I'll let you kind of think about the other direction yourself. Um, so have so I'm going to define forward move states. Just like I defined write states and read states, I'm going to define forward moving states. F, let's say 1, 1, F, 1, 2, dot, 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 up to F, um, uh, S, P, SL. I think that's all the states I need. So I keep the index. I need to keep the information about the state that I'm in, which is going to be P. That'll be right here, and then I need to increment up until S. So I know it's S plus 1, but you'll see what I mean. So then define delta prime of 0 or 1, doesn't matter. W0, 0, P, D, that's the first order of business. And I'm dealing with a 1 case, so I can assume this is a 1. That will equal, well, I want to move forward, and I want to transition into the moving state. So obviously I want to leave these alone. Whatever they were, I want to leave them what they were. Leave alone. And I want to transition into F, 1, followed by P. So you'll notice I know that I need to basically start the next simulated step in state P, and over here I'm keeping that information for later. And then that'll transition me from the write phase to the movement phase. And then once I've done that, I want to and then define delta prime of anything. Remember, I'm still, as before, just leaving everything alone. FIP, what's that going to be? Well, that should be, as long as I is up to S plus S minus 1, what I'm going to do is I'm going to say it's 0 or 1. Again, still leaving alone. Fi plus 1, and then leave P alone. For I equals 1, 2, 3, up to S minus 1. And so, that is going to get me up to S, even though I'm only defining it from up to S plus 1 because I'm incremented. So when I get to S equals 4, in my case, then this command will tell me to jump to F5, and then I'll have one more thing to do, which will be transition into the write state. So, and then finally, delta prime of 0 or 1, F SP. Once I get there, I want to move forward one more time and then transition into another read phase. So 0 or 1, again, leave alone. And then I'm going to transition into R. R0, actually, how did I start? I want to make sure I started correctly. I started in 0, 0, Q. So now I want to start in 0, 0, P. So that's going to move me forward one more tick and start me off in a new read phase, and then the process repeats. So this will have simulated a full step. And so I'm just going to go ahead and I'll just say backward phase similar. I'll let you kind of figure that out yourself. Maybe that'll be a good exercise if you want to make sure that you understood what I did here. Obviously, there's a full proof in my notes, which again, my notes are always posted in the description. So, oh, and then I forgot about halting. Really, we should talk about halting up here in the write phase, because once we finished writing, if we're supposed to halt, there's no reason to like move the cursor in any particular direction. So, back up here, once we've finished writing the symbol, once we've gotten to j equals 0, So if j equals 0 and p is a halting state, can just halt, can just stop and have m prime halt in either acceptance or rejection, or in just a halting phase if you're just caring about the output. And that's it. That's it. I mean, that was annoying, but it wasn't that bad. I just didn't want to go over it. We're not quite done. We need to analyze the complexity a little bit. So this thus we can simulate all the steps. So this is just a repeated loop where we simulate one step at a time. And so this describes a machine m prime which simulates m. Let's think about the time and space complexity. Suppose m operates in time f of n, space g of n. What's the operating time of m prime? And m prime operates in time what? Well, if f of n is the runtime, well, how many steps does it take to simulate one step? It takes, well, I have to go forward. That's going to be s steps. And then I need to go backward again. That's going to be another s steps. These aren't exact numbers, but they're more or less correct. And then I need to go either forward again s or backward again. So it's another, and then forward or backward s more steps. So 3 times. So basically 3s steps per step. So 3s f of n is the operating time for m prime. But that's a constant multiple, isn't it? And so this is still in O of f of n. I know you see a variable here, but that variable has nothing to do with the length of x. And remember, that's what we care about, the length of x. This doesn't scale any faster or slower. The runtime of this machine isn't faster or slower depending on the length of s at all. It takes more steps, but that number of steps is a constant multiple, which depends on the number of symbols that I'm covering up. And so it's still the same operating speed. And in space, well, space g of n, remember the input and output don't count. The input is going to be longer, but remember, we're not counting the input length as used space. And then in terms of, there's a siren outside. And then, in terms of how much more space I'm going to use, again, it's just one symbol. If I use g of n cells, then I'm going to use s times g of n cells, because every one cell is now s cells, but that is still O of g of n. So same efficiency. And by same efficiency, I mean it's more inefficient, but not in a significant way, and not in a way that has anything to do with the length of the input. And by the way, one last point, I promise. This proof that I gave you here is this. Let me write this down actually. Remember the linear speedup theorem, which was the theorem that told me that I don't have to care about these constant multiples. The linear speedup theorem, the proof of the linear speedup theorem, is basically this in reverse. I didn't prove the linear speedup theorem because I knew I was going to prove this, and the proof of this more or less is the proof of the linear speedup theorem. It's just instead of going from a big alphabet to a small alphabet, you're going from a small alphabet to a big alphabet and showing that the speed can go slower, that you can go faster. So I mean, up here, basically, I went from a big alphabet to a small alphabet by adding a ton of states, right? It's sort of the opposite. I can do multiple steps at once by using more symbols. And so the proof of the linear speedup theorem, you can look it up. You'll see it's almost identical to this proof, just backwards. So this proof really is the proof of the linear speedup theorem. So we have kind of both proofs at once, and that was one of the main reasons I knew I needed to show at least this, at least either this or the linear speedup theorem And showing this kind of also gives you a nice feeling of comfort regarding Turing machines and the fact that we can just switch out the alphabets willy nilly. So that's going to be the worst one. The next one, the next two robustness facts will be much easier to go through than this, I think, because there won't be any fussing about the alphabet. So two more robustness facts that aren't very fun, and then we will do something really big. We'll design a universal Turing machine.